Hi, I'm Matthew Bascom, and this is Graph Factor. This is my XORPD series where I walk you through explanations of XORPD's famous opcode book, Exchange RAX RAX. Let's get started. This program makes use of two operations and one register. The negate operation, or NEG, calculates the 2's complement of its operand, in this case the RAX register, by inverting the value of RAX and then adding 1 to RAX. The subtract with borrow instruction, or SBB, subtracts the value in the right operand from the value in the left operand. In this case, that is the RAX register from itself, but it also subtracts the value of the carry flag from the left operand. And the final result of the subtract with carry, or SBB, is stored in the left operand. So shortly after the program enters the main function on line 15, I initialized the value of RAX to hexadecimal F0 with the move instruction. Hexadecimal F0 is equivalent to binary 11110000 or 240 in base 10. As a confirmation, which is hexadecimal, we've got the least significant bit as a 0, and that corresponds to this 0 here, multiplied by 16 to the power of 0, because it's bit 0. And since the bit number 1, which is F, which stands for 15, that's to calculate the base 10 value, we multiply that by 16 to the power of 1, and 1 meaning that it's bit 1. So just below that, I have a couple additional test cases that I used to confirm the value of the carry flag and the RAX register throughout the execution of the program. But we're going to just focus on the positive value of hex F0. The XORPD challenge hex 2 code block starts at line 38. And we see that the first thing that happens is that RAX is negated. Now again, that's a 2's complement of RAX. And the way that works is it takes that initial F0 value that we gave it, and it flips every byte of the 64 bits. Right? So each in base 16, each character is a nibble, or 4 bits. So every 2 characters is a byte, or 8 bits. So every 0 in base 16 will be changed to an F, and every F will be changed to a 0. Now, since it's 2's complement, the negate NEG instruction performs the 2's complement. When we add 1 to this F value here, we have to carry the 1, and then this least significant bit, this least significant nibble becomes a 0 in the base 16. Just as in base 10 arithmetic, if you add 1 to the value of 9, you have to carry the value to have 2 placeholders. So you would carry the 1, and then you would have a 0 for the 9 plus 1 on. And let's confirm that in the debugger. So we've got our assembly program. Check my instructions here. And the compiler created the object file, and we're going to link it and create the executable. And just like in challenge hex 1, it exits quickly because it's a pretty short program. So let's open that in the debugger. Now I have a couple settings that we're going to use to make the the output a little more interesting. And so we'll be able to see the assembly in the debugger before we execute the line as we step through the program. And I'm changing the syntax flavor from AT&T syntax to Intel syntax. And finally, I'm going to set a breakpoint at the main function. And run. And so what this shows is we're starting off at the move. It shows here EAX is being placed, or rather F0 is being placed into EAX. Now, EAX is actually a 32-bit convention, but we're working on a 64-bit architecture. So the corresponding register in 64-bits is the RAX. This F0 is going to be placed into RAX, and this initial value here is just junk data. On the left we have hex, on the right we have base 10. So next I'm going to do next instruction NI, and it's going to move F0 into RAX. And we'll confirm that by looking at the registers again. And there we have our F0 in RAX. Now, if we look down here, we've got the E flags, and we're going to be focusing on this because the carry flag is going to be set in a minute here. And so now we're looking on the right-hand side to line 38. We're about to execute the negate of RAX, and so we'll see confirmation that all these bits will be shifted, or rather not shifted, they will be inverted. All of these bits will be inverted, and then added to 1 to cause this value to be populated into the RAX register. And actually, I'll print them up high because so it's more central to the screen. So we've got 240, or rather negative 240, which is the effect of the negate instruction, and its hexadecimal representation is like we calculated over here. And the next instruction will be the subtract with borrow. So just to recap on that, that negate instruction. The negate instruction performs a 2's complement negation. So the negate instruction inverts all the bits in the operand, and then 1 is added to the inverted result. For example, if the value in RAX is a binary 0101, the result of the negate instruction would be a binary 1010 plus 1 for a binary 1011. The 2's complement convention is significant because it's how the computer stores negative numbers in processor registers. Basically, if the most significant bit of the register is set to 1, then the computer knows this is a negative number. An interesting side effect of the negate instruction is that it sets the carry flag to 1 as long as the value being negated is not 0. Okay. The subtract with borrow instruction, SBB, on line 40 subtracts the right operand and the carry flag from the left operand and stores the result in the left operand. Recall that the negate instruction on the previous line also set the carry flag. In this case, SBB subtracts the value of the carry flag and RAX from itself, resulting in RAX minus 1. We will run this next command, subtract with borrow, RAX, and we'll see that the value that's populated into RAX becomes a -1. Also note that the value of -1 in hexadecimal on a computer is all Fs. And again, the reason being that most significant, if we were to take this most significant nibble and look at it in binary, the most significant bit would be a 1. Again, confirming that we're looking at the computer is looking at a negative number. As a side note, the subtract with borrow instruction is often used in conjunction with the add with carry instruction, or ADC, to perform multi-precision arithmetic. Next, the negate instruction at line 43 negates the value in the RAX register again, completing the bitwise negation. And we'll confirm that by running that right here. So next instruction. Look at the registers. And so it set it to 1. And again, that's calculating the 2's complement of RAX. Intuitively, 2's complement and the 2's complement of -1 is 1. Finally, we set the value of RAX to 0 to tell the operating system the program status when the program returns. In this case, returning 0 indicates to the operating system that the program exited successfully. Another way to look at the overall effect of this XORPD challenge is that it assigns the value of the carry flag to the RAX register. If the initial value of RAX is non-zero, the 3 instructions of this program will cause the RAX register to be set to 1. If the initial value of RAX is 0, the 3 instructions will just leave RAX as 0. That's all for this video. If you've watched this far, please hit like and subscribe. See you next time.